Chapter 7b, Electrochemistry. In the last section, we derived a few important equations to describe a chemical reaction. For example, to calculate the slope of Gibbs energy over extent of reaction, you use chemical potential of the product minus reactants. And by adding chemical potential, express chemical potential as a function of temperature pressure, we derive this important equation, and that is the reaction Gibbs energy, which can be calculated by the standard reaction Gibbs energy, plus RT ln Q. Q is the reaction quotient. At equilibrium, the slope is 0, so we have RT ln K equals negative standard state reaction Gibbs energy. We derived the Van Hoff equation to calculate equilibrium constant at different temperature and the pressure dependence. And some of these equations will also be used in the next section, and that's electrochemical reactions. Let's look at the typical redox reaction. When a zinc rod is placed inside a copper sulfate solution, with time the zinc rod disappears. At the same time, a black powder appears. What happens is there are two half reactions. One is the zinc metal loses electron to form zinc 2+. The zinc ion is soluble in the solution, and that's why you see the metal disappear, and which forms an ion that is soluble in the solution. At the same time, the copper ion in the solution, which is responsible for the blue color, gain electron, forms copper metal. And when the copper metal is small, tiny clusters, it appears as black powder. So the reaction that loses electron is called oxidation reaction, or the zinc is oxidized to form zinc 2+. The reaction gain electron is called a reduction reaction, and in a reduction reaction, the oxidation number decrease from high oxidation number to low, in this case 0, and we say copper 2+ is reduced to copper ion metal. Okay. Now later we also have a terminology about agent, oxidizing agent. For example, here zinc is oxidized because oxidation number increase to 2+. So zinc loses electron, it is oxidized. But the oxidation reaction must accompany by a reduction reaction. So it's oxidized because the reduction reaction, the zinc 2+, gain the electron to make zinc lose electron. So zinc to a copper 2+, this one is called oxidizing agent. Okay, so zinc is oxidized, zinc 2+ is oxidizing agent. Copper 2+ gain electron, so it's reduced, and zinc metal is reducing agent. All right, because this agent, it loses electron so that copper ion can gain electron and be reduced. Okay, so we can combine these two half reactions into a total redox reaction. So in this reaction, you have two half reactions. One is zinc to form zinc 2+. One is copper 2+ forms copper. One is oxidation reaction. One is reduction reaction. Okay, when you combine two half reactions, the number of electrons that is lost and gained must be the same. In the last slide, we showed a redox reaction where oxidation reaction, reduction reaction occur in a same solution. What if we can separate the two half reactions? In this setup, we have zinc metal separated from zinc sulfate solution. When zinc loses electron, the electron does not go directly to copper 2+. Instead, it has to go out of metal, zinc metal, through a wire to the copper metal. It is on this copper metal surface where the copper ion can gain electron and be reduced to copper metal. So the two half reactions, the oxidation reaction where zinc loses electron and the reduction reaction where copper ion gain electron, these two half reactions are separated into two half cells. And the combination of these two half cells is called electrochemical cell. Now note that when zinc loses electron, zinc forms zinc 2+. So the solution now has more positive charge. In order to balance the charge, we add a salt bridge. Salt bridge can only allow charge to move. So in this case, the negative charge will move to the solution to balance the charge. On the other hand, on the left side, when copper 2+ gain electron, positive charge is consumed. So the solution becomes more in concentration of negative charge. The salt bridge will provide a positive charge to balance the charge. And therefore, salt bridge completes the circuit of this electrochemical cell. Now in this cell, you have two electrodes. On the right side here, when the zinc loses electron, it's an oxidation reaction. Oxidation reaction happens on an electrode we call anode. On the left side, on the copper surface, reduction reaction occur, and this electrode is called cathode. Okay, so remember, reduction reaction electrode is called cathode. Oxidation reaction electrode is called anode. To draw the electrochemical cell is time-consuming. Chemists designed a simple method to represent an electrochemical cell called cell notation. Let's take this same reaction as an example. So the reaction involves two half reactions. One is oxidation reaction, where zinc loses electron to form zinc 2+. And the other one is reduction reaction, the copper 2+ gain electron to form copper metal. Now in the electrochemical cell, the two half reactions are separated into two half cells. So in cell notation, we just copy the reactants product. So in reduction reaction, we copy copper 2 as a reactants, and then we write copper metal as the product. Now remember, in the cell, we have a metal, all right, inside solution. All right, so this is copper, and this is copper 2+, all right, sulfate. And these two are in different phases. One is a solid, okay, copper is a solid, and copper ion in solution, so it's a liquid. Two phases. Here we use a vertical line to represent, all right, these two substances, reactant product, are in different phases. Okay. Now similarly, on the left side, oxidation reaction, we copy reactants product as same sequence as the reaction, followed by a vertical line to represent they are in different phases. Again, zinc metal in solution of zinc 2+. All right, so in a different solution, so vertical line. And also the two half cell each have its own solution that is connected by a salt bridge. Okay, So we have a double vertical line to represent this interface of zinc 2 plus and copper 2 plus are in different solution. Okay, so this complete the cell notation or cell diagram. Okay, so cell diagram have two half reactions. All right, and in chemistry convention, we always place anode on the left side. So here, left side is the anode, which represents this oxidation reaction. Cathode on the right side, which represents the reduction reaction. Okay, and the vertical line represents the phase boundary. If a metal, a solid, and liquid, so you need to place a vertical line to represent they are in different phases, and the double vertical line represents the two solutions are in different. You have two different solutions. Okay, two liquids. An electrochemical cell can be used to do electrical work, but how much electrical work can cell do? In chapter 3, we learned that the maximum non-expansion work equals reaction Gibbs energy change. Now, the non-expansion work means the biological work, the electrical work. So in this case, the maximum electrical work a cell can do equals the reaction Gibbs energy, okay, of the redox reaction. And in this chapter, we learned that the reaction Gibbs energy at any instant equals the standard state reaction Gibbs energy plus RT ln Q. Okay, so at any instant, if we know the concentration or the partial pressure of the reactant and the product, then we can calculate the Q. And then we can calculate the reaction Gibbs energy. And therefore, we can calculate the maximum electrical work the cell can do. The difference in electrical potential between the anode and the cathode is called cell voltage, electromotive force, or cell potential. All this refers to the electrical work to move one charge between two electrodes. All right, so in other words, E cell is the work per charge. So if you have charge Q, then the work should be Q times E cell. All right, so how much work is done for moving one mole of electrons? Okay, to do that, you need to know the charge of one mole electron, and that equals 96,500 coulomb. Coulomb is a unit of charge. So this is the charge for one mole of electron, and this number is called the Faraday constant F. Okay, and therefore, if you move n moles of electron, the total work should use number of moles n times Faraday constant, and this gives you the total charge. And then you times E cell, and that is the total work for moving n moles of electron. Suppose we have a redox reaction defined as here, which involves n moles of electrons. For example, the reaction we already know, zinc plus copper 2 plus, forms zinc 2 plus and copper. So in this reaction, zinc loses 2 electrons, and the 2 electron goes to copper ion to gain these 2 electrons. So in this reaction, n equals 2. Okay, and alpha is 1. These are the coefficient. Beta is 1. Gamma is 1. Delta is 1. All right, so here this is the general equation reaction, and you have n electrons, moles of electrons. Okay, in this chapter we learned that at any instant the reaction Gibbs energy is calculated by the standard state reaction Gibbs energy plus RT ln Q. Second law tells us that the reaction Gibbs energy is the maximum non-expansion work. In this case, is the electrical work. And in the last slide, we show that the electrical work for n moles of electron is n times Faraday constant, which is charge, and then times E cell. Okay. Now, if the reaction is spontaneous, then delta G is less than 0. So this is a negative number. To make E cell positive, we add a negative sign. Okay, so negative NFE. Okay, that gives you delta G. Similarly, at the standard state, the reaction Gibbs energy should be negative NFE at the standard state. So this is a standard E cell. All right, that gives you the standard delta G. Okay, so this equation, if we divide by negative NF, all right, then the left side becomes E cell. Okay, let's allow you to calculate E cell should equals to E cell at the standard state minus, so positive becomes minus because you divide by negative NF. So RT divided by NF times ln Q. All right, this equation is called the Nernst equation. So Nernst equation allow you to calculate E cell at any instant if we know the Q, reaction quotient. All right. Also note the standard delta G is related to standard E cell. Okay. In the next slide, we show that because standard delta G relates to equilibrium constant, so E cell can also be calculated by K constant. In the last slide, we show that the standard reaction Gibbs energy equals negative NFE at the standard state. The standard delta G equals negative RT ln K. And therefore, we have this equation. Negative NFE at the standard state equals negative RT ln K. So equilibrium constant and the standard E cell are related. Okay? So thermodynamic data such as standard delta G or equilibrium constant can be conveniently determined by measuring the standard E cell. Since each electrochemical cell contains two half cells, it is useful if we know the potentials of two half cells called half cell potential. The half cell potential is measured by combining an unknown half cell with a reference half cell. Usually, it's the standard hydrogen electrode. Now, here is the cell notation for the standard hydrogen electrode, which involves hydrogen gas and a proton in a solution. Now, because neither hydrogen gas nor the solution conduct electricity, we need an inert electrode, and that is the platinum. So platinum is inert metal that does not participate in a redox reaction, but provide a surface for the redox reaction. Okay, and now because we are only concerned about the relative potential, all right, and therefore we can conveniently define the standard hydrogen electrode as 0. Okay, potential is 0. So in order to measure, for example, copper electrode, we combine the copper electrode with the standard hydrogen electrode. All right, we measure the cell potential, and that gives you the half cell potential of copper because the hydrogen electrode is 0. Okay, also notice that in chemistry convention, we always place the unknown half cell on the right side and hydrogen standard cell on the left side. That means that before we measure, we already assume the unknown half cell is a cathode. The reaction is a reduction reaction. Okay, so we assume this is a reduction reaction, and therefore the measured half cell is also called reduction potential. Now, if measured number is positive, that means assumption is right. This half cell is reduction reaction. Okay, now if the number is negative, and that means it's actually an anode, so it's oxidation reaction if you combine with hydrogen half cell. Here shows some standard electrode potentials. Remember, these half cells potentials are measured by combining this half cell with the hydrogen electrode and assuming these unknown half cells are reduction reaction. Okay, they are cathode reduction reaction. So if number is positive, that means the reaction half cell is a reduction reaction. Fluorine gain electron, all right, and the hydrogen will be lose electron. So it should be hydrogen gas lose electron to form hydrogen proton. Okay, so if you combine these two, all right, that's negative, positive. Now, if the number is negative, then that means if you combine this half cell with hydrogen electrode, it's not reduction but oxidation. So lithium lose electron. Okay, the real reaction is this one with hydrogen gain electron. With the half cell potentials described in the last slide, we are now able to calculate the cell potentials. Suppose there's a electrochemical cell described by this cell notation, which include a cathode, all right, and an anode, and both half cell potential are given as reduction potential, okay, as if they are reduction reactions. But we know that one of them, the right side, is the cathode. Okay, this is the cathode, and this should be anode, should be an oxidation reaction. So when we calculate delta G, all right, the delta G is negative NFE, but on the left side you should add a negative sign because the real reaction is opposite of this reduction reaction, and therefore the total delta G is the cathode, all right, minus the anode because you have a negative sign. And so that leads to, this leads to an important equation that E cell is calculated by the cathode half cell potential minus anode half cell potential. Or we can write as E cell equals the right side, which is the cathode half cell potential, minus left half cell potential, which is the anode half cell potential. Sample question. From the given standard potential, okay, you have two of them, predict whether the following reaction will be favored. All right, so in this equation, zinc 2 plus becomes zinc 0. So the zinc 2 plus gain electron. It's a reduction reaction. So reduction reaction is a cathode. So if the reaction is as written, then zinc 2 plus to zinc is a cathode, and the copper lose electron to form copper 2 plus. That's oxidation reaction. Oxidation reaction is anode. According to the equation we derived in the last slide, the cell potential for this cell is the cathode minus anode. So it should be zinc cathode minus copper anode, and negative 0.76 minus 0.34, and that gives you a negative number which is less than 0. Remember, delta G is negative NFE. So if E is negative, then delta G is positive. A positive delta G means reaction is non-spontaneous. Okay, so remember, a positive E, okay, give you a negative delta G, which is spontaneous. A negative E give you a positive delta G, which is a non-spontaneous reaction. And therefore, the reaction as written is not spontaneous. All right. Instead, you should opposite. So the zinc, instead of zinc 2 plus gain electron, should be zinc lose electron. It's an anode. And the copper 2 plus gain electron. That's a reduction reaction. Okay, so copper 2 plus will be reduced while zinc will be oxidized. And because copper 2 plus is reduced, zinc is called a reducing agent. Okay, so zinc has a lower potential. All right, so we can say the half cell, okay, here has a low chemical standard potential, reduce the one with high potential. All right, so it's a standard cell potential. So low, reduce, high. How do you calculate the equilibrium constant for a redox reaction? First, we need to identify the two half-cell reactions. So for this particular reaction, one is copper ion goes to copper 2 plus, okay, 1 plus to 2 plus. That's lose electron. It's an oxidation reaction. It's an anode. So anode should be on the left side. So left side is the anode, lose electron, okay, 1 plus goes to 2 plus. Because both ions are in solution, does not conduct electricity. So if you write a cell notation, you need to add an inert metal as an electrode, okay, to provide surface for electrons to move. Okay, so that's the left side anode, and the other half reaction is copper 1 plus goes to this copper 0 metal, and that's reduction reaction. Reduction reaction is a cathode, so on the right side, so copper plus goes to copper metal. Now in this half cell, copper metal itself conducts electricity, so you don't need an inert metal for the electrode. Okay, so next we are going to find the half cell potentials for these two cathode and anode. So in the standard cell potential table, okay, we find for the copper half cell potential, we have copper 2 plus goes to copper ion. Note that here is written as reduction. Okay, even though in the reaction is oxidation reaction, but the table listed as reduction reaction. So it's 2 plus goes to 1 plus, and the reduction potential is 0.16, and the cathode is copper ion gain electron. That's a reduction reaction, forms copper metal, and the reduction potential is 0.52. And with these two half cell potential, we calculate the cell potential is use the cathode. Remember, cathode minus anode, or right minus left. So right 0.52 minus left 0.16. That give you 0.36 volts. Now with this, we now can calculate equilibrium constant. Remember, delta G is negative NFE. Okay, so this is the E here. We just calculated, so we can calculate delta G, but delta G is also equals negative RT ln K. So these two are the same. All right, so we can calculate the K using cell potential. So ln K equals NFE divided by RT. So plug in all the data. All right, F is the Faraday constant. So the answer is K equals 1.2 times 10 to the 6th power. In the last two slides, we show that in a same chemical electrochemical cell, the cell potential can be calculated simply by the cathode standard cell potential minus anode. Okay, cathode minus anode. But if the half cell potentials do not belong to the same cell, then you cannot use cell potential. You have to go to Gibbs energy. So here is example. Given the standard potentials of two half cells, okay, copper 2 plus to copper metal, copper 1 plus to copper metal, these are the standard potentials. We want to calculate each standard potential for a different half cell, okay, copper 2 plus to copper ion. All right, so first we write the reactions. So for the first half cell, the reaction is 2 plus to metal 0 gain 2 electron. All right, and the listed reduction potential is 0.34. And the second one is copper 1 plus gain electron to form copper metal, and the reduction potential is 0.522 volts. Now, what about the new half cell potential reaction? It's the actually you use A minus B. Okay, when you use A minus B, then 2 electron minus 1 electron give you 1 electron. The product cancel each other, and 2 plus minus copper, you can move to the right side, becomes a product. Okay, so this cell reaction, half cell reaction, is obtained by A minus B. Now, can we use the standard cell potential for A minus B? And the answer is no, you can't. All right. In fact, you have to use Gibbs energy. So we calculate Gibbs energy for these half reactions. For A, Gibbs energy change is negative N, which is 2 electrons. F is here, and the E is given. All right. For the second reaction is negative N is 1, so 1 electron, and F and E. All right, so that's the delta G for second reaction. But remember, Gibbs energy is a state function. All right, so state function only depends on the initial state, final state. So if a new reaction is obtained by A minus B, then delta G for this new reaction can be calculated by the Gibbs energy of A minus Gibbs energy of B. So that's the negative 0.68 minus negative 0.522 give you positive 0.522, and that give you negative 0.158 times Faraday constant as the Gibbs energy change for the new reaction. So what is potential, standard cell potential? Remember, delta G equals negative NFE of the cell standard potential. So this can be calculated. All right, so delta G divided by NFE. N is 1, and that gives you 0.158. All right, so for this type of question, you need to use Gibbs energy. And even though standard potential, you cannot add or subtract, but the Gibbs energy can.